Welcome back to the hidden geometry of intelligence. If you took calculus in high school, you almost certainly remember the derivative as the slope of a tangent line touching a curve. You drew tiny triangles, calculated rise over run, and memorized rules like x squared becomes 2x. While this geometric view is mathematically true, it is often too static for our needs. In the world of machine learning, we aren't just observing static curves. We are operating a machine. We need to move from geometry to mechanics. Think of a mathematical function not as a line on paper, but as a physical box. It has inputs and it has an output. And the variables? They aren't just letters, they are knobs. The input x is a dial we can twist. The output y? That is a gauge. It tells us the current state of the system. In AI, this gauge often represents the error or loss. So, what is a derivative in this mechanical world? It is simply a measure of sensitivity. It asks a simple question. If I nudge this input knob a tiny amount, how violently does the output gauge react? Sometimes the machine is stiff. You turn the knob, but the gauge barely moves. This is a low derivative. And sometimes you are in a dead zone. You turn the knob, and nothing happens. The sensitivity is zero. Let's make this precise. Let's bring back the graph, but keep our mechanical intuition. Imagine our knob controls the x position. Currently, we are at x equals 2. We nudge the knob by a tiny amount, let's say 0.001. We call this nudging dx. Because of the machinery of x squared, the output height rises. We call this rise di. At this specific setting, the output rises 4 times as much as the input. The ratio is 4, that is our derivative. This amplification factor tells us that this specific knob is very powerful right now. A small change here matters a lot. But real neural networks don't just have one knob, they have millions. Imagine a massive mixing board. The output error depends on the combination of all these settings. This is where high school calculus usually stops, but where AI begins. If we start twisting all the knobs randomly at the same time, the result is chaos. We can't tell which twist caused the error to drop. So we use a disciplined strategy called the partial derivative. We freeze everything except one. We ask, holding everyone else still, what is the sensitivity of the error to this specific guy? We give it a virtual nudge. If the error drops, we know this knob is responsible. We turn it slightly. Then we freeze him, move to the neighbor, and repeat. We are building a map of sensitivities. Let's see this in the context of a single neuron. The building block of the brain. The circles on the lines are the weights. These are our knobs. They control how much signal gets through. Currently, our neuron is outputting 0.2, but the target is 1.0. We have a large error. To fix this, we need to know, should we increase W1 or decrease it? We calculate the derivative. If the derivative is positive, increasing the weight increases the output. Since we want more output, we turn the knob up. This process of checking the sensitivity and adjusting the knob is called descent. We are descending the mountain of error. But there is a trap. What if the derivative is 0? If the sensitivity is 0, nudging the knob changes nothing. The machine doesn't know which way to go. It stops learning. This is the vanishing gradient problem, a major hurdle in deep learning history. It's like trying to fly a plane with disconnected controls. But when it works, it is beautiful. Training a network is simply performing this sensitivity check on billions of knobs, over and over. Nudge, measure, adjust. Nudge, measure, adjust. Until the error hits 0. Next time, we will organize all these individual sensitivities into a single powerful arrow, the gradient vector.